So this video is about function transformations. Let's see. And this is actually made for pre-calculus, but this concept, you first do a little bit in Algebra 1. We do a whole unit on it in Algebra 2, and then just continue that unit now in pre-calculus. So to get started, let's look at this page that has all of these basic graphs on it. Here we go. It has all of these basic graphs. These are all the parent functions that you need to know. There are 9 of them. Now, I would say all but maybe one of them you would have seen last year. So really we're only adding one to what you should have already done in Algebra 2. So let's kind of look through the basics. So you may remember that if it's a basic line that goes through the origin, the equation is y equals x. If it's a basic parabola, again, that goes through the origin, we would say it's y equals x squared. And remember, the thing about the parabola is from that vertex you go up 1 over 1, unless, of course, we change the number in front. Same thing about the cubic graph. Notice it goes through the origin. It has this up 1 over 1 point on both sides. This is x cubed. And then we have the absolute value graph. So the absolute value of x, and again, goes through the origin. It has that up 1 over 1 point for each one. This is your square root of x graph. Goes through the origin, has the up 1 over 1. So notice I'm putting those key points on every single graph. These are kind of the key points that I'm looking for to make sure that you have an accurate graph. Okay, this next one is the rational function. This is y equals 1 over x. And remember, the thing about this one is it has an asymptote here on the x-axis and an asymptote here on the y-axis. And the asymptote means that, notice when you draw the graph, it doesn't actually touch that asymptote. It gets really, really close to the y, it gets really, really close to the x on both pieces, but it doesn't actually touch. So that's kind of the picky parts that I'm looking for. And then when we got to second semester, and the very last thing we brought in were the exponential and log graphs. So this one is our exponential. We would call it e to the x. It might be 2 to the x or 5 to the x. So in other words, it doesn't matter what the base is, as long as it's to the x, we would call it an exponential graph. Okay, and then this one is our log graph. So we're going to call it natural log of x. It might have been, let's say, log base 3 of x or log base 5 of x. And we kind of talked about logarithms last year. But for pre-calculus, we're going to focus in on this, what's called the natural log. And we mentioned it last year. And then the last graph is a semicircle. And this is the one I'm not sure you would have done in Algebra 2. But basically, the equation is the square root of the radius squared minus x squared. Notice all of that is under the square root. And so when we say radius, remember the radius is the distance from the origin to the outside. So since this has a distance of 2 in every direction, on this one we know the radius is 2. So if I were asking for the specific equation of this graph, it would be the square root of 2 squared, so 4 minus x squared. So this is the specific equation for this graph, whereas this one is kind of the generic equation for any semicircle. And then you would just insert whatever the radius is. All right, so those are the basic graphs that you just need to know. All right, so let's do some practice on this. Okay. So on this, we're going to just actually practice the graphing. Okay, so on the previous page, I wanted you to identify. So now let's just practice the graphing. So for example, when you graph y equals x, remember f of x is the same as y. Since you know it's the line, I would expect you to put on the point at the origin, put on the up 1 over 1, and then you can draw your line. Now, since it's a line, I mean, if you wanted to, you could draw as many points as you want, right? But that's only on the line. Okay, and then for number 2, for the parabola, so remember I would expect you to put on that point at the origin. I would expect the up 1 over 1, and then just draw the graph as best you can. For the x cubed, I would expect the origin, the up 1 over 1. And remember, when you draw this, you're not coming, it's not straight down, straight down, straight down. That's not what the cubic graph looks like. It's coming down this direction. When you get here, you turn and kind of go through, and then at that last point, you turn and kind of go down. So I know it's going to take some practice, but I expect these to be somewhat decent looking graphs. Okay, then for the absolute value graph, again, the origin, the up 1 over 1 on both. Do the best you can to try and make those be some nice straight lines on both sides. Whoops, some nice straight lines on both sides. Let's see, something like that. And then for the x cube graph, again, you've got your point at the origin, you've got your up 1 over 1. And again, it's not just straight to that point and straight out, although that's close. If you imagine, if you were to have drawn a full parabola, the square root graph is basically just that top half. So you're coming up through, this pen is terrible. Let me see how I can do here. Let's see if this is any better. So you're coming up through and over. All right, for the e to the x, so on this one's different because you don't have the point at the origin, but you actually have the point right here on the y-axis. And remember this one, it comes down, oh, that's terrible. Comes down like this. It gets really, really close to the x-axis and doesn't touch it. I didn't mention it earlier, but the x-axis is actually an asymptote because the graph gets really, really close but doesn't quite touch. And then on the log graph, where the exponential hit the y-axis at 1, the log graph hits the x-axis at 1. Again, the exponential had an asymptote on the x-axis, but the log graph has an asymptote on the y-axis. So when you draw this graph, it comes in, gets really, really close to that y-axis and doesn't quite hit it. Okay, and like we said, the 1 over x had asymptote on the y-axis and another one on the x-axis. And actually, if you're drawing it, you have an up 1 over 1 point, just to kind of give you an idea. So this graph comes down and through. That's terrible. Oh my gosh, I'm having a terrible time drawing these graphs with this pen. So it's going to do something like this. And then again, get really, really close without actually quite touching. Okay. And then this last one, remember this is our semicircle. That 4 means the radius is 2. So the radius is, because that 4 is your r squared. So if I have a radius of 2, that means it's centered at the origin, but you're going to go up 2, out 2 in both directions. And that is actually the semicircle. I just put the center on so I could judge where to go out to from. Okay, so those are all the basic transformations. And what we're going to do with those, those are all the basic parent functions. And what we're going to do with those is move them around, again, just like you did in Algebra 1, just like you did in Algebra 2. So remember the idea, if you add or subtract a number at the end, then you move the whole graph up or down. So for example, if I look at number 1, on number 1, I see the x squared. That's how I know it's a parabola. But then that -4 is out at the end. So that parabola is moved down 4. So the entire thing is moved down 4. So now there's your vertex. It still has the up 1 over 1. It's just that now when I draw it, it's going to go all the way down to that number. Or when you look at number 2, so first you identify which parent function it is. Oh, this is the square root. It's not the semicircle because it doesn't have an x squared in there. So this is the square root graph. So just so we can kind of be thinking out loud, remember the basic square root is something like this. Okay, but notice in this case, it has a +2 on the inside, not at the outside. So this is the kind of situation where you've got some number being added or subtracted on the inside of the graph. And so remember, if it's on the inside, it moves either left or right. And remember, it's like the opposite of what you would think. So on this one, there's my square root graph. From that origin point, I'm going to move the entire thing to the left 2 because it's a plus. That means it moves to the left 2. So now that point is here. I still have my up 1 over 1. So now it's going to look something like that. Not great, but it's decent. Okay. Now, number 3 puts both of those together. So I know it's a cubic graph because I see the cubic. So where it used to be at the origin, that -2 means it's moved 2 to the right, and then the -1 means it's moved 1 down. So that's the center of the cubic. I still have that up 1 over 1 point so that I can kind of judge my basic shape. Okay. Number 4, I see the 1 over x graph. So I think about this is the one that has the asymptotes. And so where the center of those 2 asymptotes was at the origin, now I'm going to move it 4 units to the right. So the -4 is 4 units to the right, and at the same time, 3 units up, 1, 2, 3. So that means that is now the center of my asymptotes. So from that point, I want to draw in my asymptotes, extend them beyond the graph so that you can see the full thing. And now, from that point, I've got my up 1 over 1 in both directions. I can draw my basic, okay, this is not a right turn. I don't want you to think I just came straight down and over. It's actually curved. Something like that. Okay. On number 5, so this is my exponential graph, right? It's the exponential graph that normally is right here at 1. So from that point, not the origin, from that point, I'm going to go 3 units to the left. That's the +3. 1, 2, 3. That takes me here. And then from that point, I'm going to go 5 down. So 1, 2, 3, 4, 5. So this is the point that used to be right there on the y-axis. And remember how the exponential has the asymptote just below that point. So when I draw that graph, it's going to look something like this. Level off at that asymptote. Okay. Then I have my log graph. So remember, the basic log graph went through here and it had that asymptote right here. So the basic log graph, remember, did this kind of thing, the basic log graph. So what does that negative on the inside do? Okay, well, you may remember from last year, we said if there's a negative on the outside, then it flips across the x-axis. So flips across x-axis. So what would you speculate is going to happen if the negative's on the inside? Well, it's going to flip across the y-axis. So the negative on the inside, on the x, flips across the y-axis. Do you see that's what we have here? That negative is on the inside as opposed to out in front, right? Okay, so that means I'm going to take that graph. I'm going to completely flip it. It's like you're folding it on the y-axis. So that point that's there on the x-axis, if I flip it across, that point is going to land right here. And now my graph is going this direction, right? That's me flipping it across, but I still have that +2. So I need to move that whole thing up 2, so up 2. So I have got that same shape, just moved up 2. So it's going to be something like that. I'm going to get rid of all this. That kind of helped me get there, but that's not actually part of the graph. Okay, now you look at number 7 and you're like, what in the world? Well, if it's just an x, no x squared, no x cubed, no absolute value, no square roots, isn't it just a line? In fact, hopefully, doesn't this just look like mx plus b, right? So y-intercept of -4, a slope of 3, 1, 2, 3 over 1, and you can do that as many times as is helpful. So when I draw that graph, it's just going to be the line. So don't forget that lines still exist. How do you recognize them? Well, because you don't see anything on the x. It's just like an x to the first. Okay, when I look at number 8, first thing you need to do is identify which parent function. So this is the absolute value. This is the one that's the v, right? but I'm going to not only move it 2 to the right and move it 1 up, but notice that negative out in front. Doesn't that negative out in front mean it's going to be opening down? So it's coming down this direction. And remember, these are linear pieces, so these should be straight lines. There's no curves to them, right? So these should be straight, whoops. These should be straight lines, something like that. Okay, and then my last one. So because it's a square root, but remember there are two of them that have square roots, right? There's the one that just does this, and then there's the semicircle. Well, because this has an x squared under the square root, that's how I know it's the semicircle, and that 9 is your r squared, so that means the radius is 3. So here's my center. I have a radius of 3, so from that center, I'm going to go out 3, and then I can draw my semicircle. Okay? Now, I'm about to show you 2 more transformations that we did not do last year. So here comes the pre-calculus part. And that is, what if you have an absolute value of the entire function? So like, what if I have any random function, I don't know, maybe it's some parabola, that's been moved to the right and, I don't know, down 1. Well, what this means is, what if I put an absolute value around the whole thing? What if I put an absolute value around the whole thing? That's what this first one means. Okay, well, think about it. What does absolute value mean? It means turn everything positive, right? Turn everything positive. So that means you're going to, whatever was positive, meaning whatever was above the x-axis stays. So I'm going to write it this way. I'm going to put here, keep stuff that was above the x-axis. Oops, if I could write, keep stuff above. I'm trying to make this be basic, okay? So anything that was above the x-axis, you keep, you leave it alone. But anything that was below, that means it was negative. Anything that was below gets flipped up. So stuff below flips up. So for example, I've got this particular graph, given the f of x below, graph the following transformations. Okay, so if I want to take the absolute value of the whole thing, so in this case, I would keep the stuff that was above. So just to do it on this graph, here's the stuff that's above, right? This is above the x-axis, and this is above the x-axis. And then I take the stuff that was below the x-axis and I flip it up. So instead of being down here at -4, this point is now up here at +4. So I just flipped it up. Instead of this point being down here at -2, it's going to flip up here to +2. And so now that graph, and only that graph, what I've highlighted in pink, that is your absolute value. If I wanted to transfer it over here on this one, I could just put on those individual points. Let's see, that's at 4 and all the way out at 6. So that's like right here. And then I have the point down here at 4. And then it went up 2 and then back to the origin. So this is just kind of helping me see, where that graph was. And then it was over here at 3, 2. And then from there it came down to the origin and then back over to 6, 1. Something like that. Something like that. Okay? So that's if you have the absolute value of the whole thing. So just to kind of show you how that works down here. So look at number 1. Number 1 says, forget all the absolute values. What if this is just a basic parabola? What if it's just a basic parabola? So this parabola is moved 2 units to the right and 3 down. Okay, I know it's the parabola that just has the up 1 over 1. So if it's the basic parabola, it's something like this. Okay, so what this says is, what if I take the absolute value of the whole thing? See, it's the same parabola, but I'm taking the absolute value of the whole thing. So that means the part that was above the x-axis. So the part that was above the x-axis was something like this, over here between 3 and 4, something like this. Okay, and then the part that was below, so where the vertex was down here at -3, if that gets flipped up, now that vertex is up here at +3. So if I take the stuff that was below and flip it up, that's my new graph. Okay, and then on number 3, notice now they're saying, hey, what if I have the absolute value of just the inside? Okay, so absolute value on just the inside is different. On these, instead of keeping the stuff above, you keep the stuff to the right. So keep right. So anything that was on the right, meaning the right side of the y-axis. And then instead of flipping the stuff that was below, that right, you mirror to the left. So I'm going to say keep right and mirror to left. So on this first graph, okay, so now I'm going to get rid of this here so that you don't think that was the final thing. Okay, so go back to my original graph. All the stuff that was on the right, so that would be this stuff. All the stuff that was on the right, you keep. So I'm going to transfer that over here. It was at the origin. It went over to 3, -2, back up, and then right there. So this is the exact graph that that I have on the big one. And so I keep the right, and now don't look at the original. Now I'm going to mirror that to the left. So it's like I'm going to fold it across the y-axis. Well, if I fold it across the y-axis, over here at +3 is now over here at -3. So that first piece folded over. Over here where it's at +4, now it's going to be over here at -4. So I'm just flipping all of the individual points. And where this one was over at +6, now it's over here at -6. So do you see I've kept the right side? That was this piece. Here's where I kept the right. And then I took that and I took that right side and I mirrored it to the left. Okay? So hopefully that gives you a little bit of an idea of absolute value transformations.